Okay, guys, think back to the last time that something surprised you. Huh? What made it surprising?
It was not expected.
Unexpected?
Yeah. Are you supposed to be screen sharing?
This is twice this has happened, yeah. You guys, I'm only giving structured notes in 2 classes today, and I failed twice. I'm telling you. Look at also how I'm spelling unexpected.
It's alright.
Don't look at me like that.
You're doing great.
Oh, that was really sweet. Okay. It's a person in second period called it extreme, right? Like if you're expecting one thing and it's extremely different than what you expect. So like if it's close to what you would expect, it wouldn't surprise you. But so it'd have to be kind of extremely different from what you would expect. Yeah? Everybody good? Okay. So, you guys, think about the cost of a candy bar. How much do you guys think if you walked into Speedway and get a regular size candy bar, how much it would cost?
Like $1 or something. $2.
About $2? Okay. All right. So, let's pretend you guys give me $20. Each one of you gives me $20. And because I'm going to the store and you said, will you give me a candy bar while you're there? And I say, sure. And then I come back with your change. Everybody good? I would like you to circle the different change amounts that would be surprising to you. How many of you circled 1809? 1757. $5.12. 878. 1227. 1962. I would circle 1962. That you guys, that would equal a 38-cent candy bar. And if that's the case, sign me up. What about 1432? That would surprise you too, yeah?
I'd say king size.
I don't know. I love 14. Inflation.
So this one's a maybe.
Yeah.
And why is this one a maybe? Yeah, certainly inflation is a thing. That is a $5.68 candy bar. There's no candy bar in the world I would buy for $5.68. That's a lot of money. But I come from a place where, like, when I was your age and really interested in buying candy, it was 50 cents a piece. And for Mr. Richards, when he was in high school, $0.25. But you could also get a gallon of gas for $1. So, you think about it. It's different, right? Okay. All right. So these ones, not surprising. These ones, surprising. This one is questionable. Okay. So can you guys put just like into layman's terms the why of that? Why are these surprising and these not?
They're either really low or really high.
They're lower or higher.
Getting back.
So they are extreme. Yes? They are extreme if our expectation is true. Everybody with me? Okay. So we're going to start operating on a candy bar costs $1.99 because I think that is actually pretty darn close to what Giant Eagle charges for a pack of peanut M&Ms. I'm not saying I'm speaking from experience, but I know a lot about peanut M&Ms.
Okay. What about peanut butter?
They're almost as good as peanut M&Ms.
Dark chocolate peanut M&Ms with the purple
Meh.
I like
Meh.
regular. I
What?
like mini one.
I can't even talk to you.
No, those are better ones.
Regular M&Ms. Plain M&Ms.
I love a good regular M&M.
I like minis.
Caramel. But I like the peanut butter M&Ms. I love peanut butter.
There's so much extra sugar. Like the peanut M&Ms are healthy for you because they have protein in them.
But the peanut butter M&Ms.
And
You
so
guys,
are
the
and
fact
so
that
are
the
dark chocolate. Like,
the fact that you guys didn't even think you guys peanut M&Ms are also not good for you. Okay? Like,
Is the red bag this peanut butter?
yes. You want to know the best bag. I've only seen them at Giant Eagle, but I'm sure they exist elsewhere. It's a third plain, a third peanut, and a third peanut butter M&Ms all in one bag.
that sounds kind of good.
It's like I never would have been somebody who would think that mixing those together would make them better or worse.
So then you'll eat regular M&Ms.
Yeah, because like getting bites of peanut and peanut butter at the same time.
All right.
Hold on. I gotta fact check this. It does exist.
I'm standing right here. I'm telling you I have purchased them. This is a first person account of this bag of M&Ms.
Are they actually split up? No.
Mm.
They're scattered? So you don't know?
You pour some in your hand, you pop it in your mouth, and you're like, oh, I've got explosions of all these different great flavors inside.
Well,
Since
it's just-
Mr. Emergis is not here, I think you should get one of those dispensers and just put
Mhm.
in M&Ms.
I would
So
I would
good.
go in there and
Yeah, no.
No, when you had the bags. Up there, those extras.
You mean the ones that are sitting in the jar of candy in the back of the room?
Oh, can we all drop one?
Maybe if I get through what I want to get through, you guys can have some
Okay,
candy at the end of the
alright.
class period.
I'll take that. Locking in.
Okay. All right. So are you guys with me that this would mean our expectation is that the true mean is 1.99, $1.99. If I take a sample, let's imagine each of us goes to a different location in Grandview. We've got the Speedway, we've got the Gecko, we got Giant Eagle, we got the other Gecko, the UDF on King, and Sheetz sells M&Ms?
Probably.
Oh yeah, they would. Yeah. Sheetz and
Kroger. Did you say that?
Kroger, CVS, Walgreens, Big Lots. Everybody goes and buys in one package of M&Ms, right? We all get the same size package because that would be important. And we find the mean of our sample. And we find the mean price. Everybody good? Okay. If the mean of our sample was 204, would that make you question whether that $1.99 is true? No. No questioning. Okay. What if the mean of our sample was $1.75? Would that make you question it? No. What if the mean of our sample was $2.57? Eh?
50-cent difference.
25% difference.
50 cent, I said.
I know, but that's 25% higher than $2, right? What if our sample was $1.51? We're still good. All right. What if our sample was $2.99?
Maybe.
it's getting a little high.
What if our sample was $1.05? Would that make you question the $1.99 being the actual average? Yeah, like both of these would make me go, huh? That doesn't feel right. And then which one of these is actually true? The actually true piece of this would be whatever we get for our sample. Okay? Do we know that our expectation is true?
Oh.
No. Think about the last time you were surprised. What you expected didn't happen. Right? Okay? The expectation is, what we're doing is kind of saying, let's see if our sample makes us doubt our expectation. And if our sample makes us doubt our expectation, like if this was the sample I got, I'm saying that isn't true. It's probably that the actual mean price of candy bars is lower than that $1.99. Cool? Okay. So, we are going to learn a new thing called a hypothesis test or a significance test. When we do, there's going to be two methods we learn for significance tests, okay? One is called the traditional method. One is called the p-value method. So each page of this, we're going to focus on a different step of the traditional method. And then after that, after we get through the traditional method, then we'll talk about the p-value method. You're going to be expected to know both methods, okay? But they go hand in hand. Now, Haley and Charlotte, this looks different than when I taught it to you last year. Ever so slightly different. Because there's like two fields of thought about writing your hypotheses. Like you guys remember doing null and alternative hypotheses? That's what we're about to do. Columbus State follows one school of thought. College Board, when I teach AP, follows a different. I taught you guys the College Board way. So it's going to look, but the only difference is like a greater than or less than sign. That's it. Okay? All right. All right. So we're always going to start with two hypotheses. The first one is called the null hypothesis. The second one is called the alternative hypothesis. And my null hypothesis, we write as a H0. Our alternative, we write as an HA. We kind of make those little subscripts. I'm probably not going to be picky if you make them subscripts or not. Okay? And our hypotheses are about parameters. What do parameters measure? Population. The two parameters we've been working with are mu and p. Depending on, are we talking about a mean or a proportion? The null hypothesis is kind of going to be we're going to think of it as the expectation. And the alternative is going to be the surprise. Which is what we're going to conclude in the end if our sample is surprising. The other thing to know is the null hypothesis has equal in it.
Is equal what?
In it.
Wait.
That'll make sense when I show you how to do it. Okay? And you guys, both hypotheses cannot be true at the same time. Is everybody with me? So they're opposites of each other. All right. So when I look at this, if we want to show that the mean weight of a mouse is more than 15, are you guys with me that I would write that as mu is greater than 15? Does this have an equal in it? No. Okay, that means my alternative hypothesis will be mu is greater than 15. What would my null hypothesis then be? Well, it would be the opposite of greater than 15. Mu would be less than or equal to 15. This one has the equal in it. Does this make sense, Ronan, now? Like when... And so far, how are we feeling? So the big difference is last year, guys, I made you write an equal to here, not a less than or equal to. That's really the only difference. And if you wrote the equal to, you won't, I'm not going to ding you for it, because if that is habit for you, that's fine.
Wait, what?
I taught this to the FST kids last year, and it looks different. But like the online homework and everything else matches this formatting. So, okay. All right, you guys, null hypothesis for an alternative hypothesis for this one. First of all, what's kind of what we have here? Proportion lower than 40%. Is everybody with me? Strictly lower than. That would be P is less than 0.4. Because that less than does not have an equal to in it, it is my alternative. What's the opposite of being less than 0.4? Greater than or equal to 0.4. And do we all understand why I used P here? Talk to me.
How is P is greater than or equal to 0.4 expectation? I don't understand.
So the easier, think of it this way, if we want to show that something is lower than 40%, it would be unexpectedly low, right? So the unexpectation would be lower than 40%.
The expectation?
So in order for it to be surprisingly low, for us to conclude that it's lower than 40%, we would need an extremely low percent.
Okay. Alright, just keep going.
All right. Does everybody understand why I switched to P instead of mu for this one? Okay. Last one. How could I write different from? Mu is not equal to 9. So what would that make my null hypothesis?
It's greater than or less than 9. Right?
No. This is essentially mu is greater than 9 or mu is
yeah,
less than 9.
sorry.
So it would just be mu equals 9.
Sorry,
Yeah,
just mixed it up. Could you also write then alternative hypothesis as is greater than or less
Yeah, but yeah.
than? Either way.
Yeah. Okay. All right. So these are going to be the same examples, right? But this time we are practicing the next step, which is called sketch the sampling distribution. And we're going to find something called a rejection region. Okay. So the sampling distribution, you guys might not know this, but you are already familiar with the sampling distribution. Okay? The sampling distribution is either going to be a Z or a T distribution, like the Z's and T's we were using last week. Okay? So this is the same set of examples. So for this one, we had the null was less than or equal to 15, and the alternative was greater than 15. Okay, so every sample has something called a test statistic. We're calculating those on the next page. Okay? So the test statistic is either going to be Z or T. Now, once you have your test statistic, you compare it to the other possible Z's or T's. So, in this particular case, my test statistic would be Z. How do I know it's Z? I have the population standard deviation. When I have that population standard deviation, I use Z. Okay? And if we're using Z, we have the mean is 0 and the standard deviation is 1.
How would the standard deviation be 1?
Because this is not the population. This is a graph of all the possible means. The Z statistic of all the possible sample means we could get. And anything that's Z has a mean of 0 and a standard deviation of 1. Anything that's T is centered at 0. And instead of using a standard deviation, we use those degrees of freedom.
So wouldn't it be the little like subscript of an X bar under the 7 dBs?
No, because it's actually the standard deviation of the Z scores.
Okay, would it be? Okay.
So if I were... The picture you're thinking of, and it's kind of hard to say because we don't know the sample size, right? So you can't divide by the square root of n. It's kind of a problem. So the idea of when we find this test statistic, the way we calculate that z-score for our sample means we want to compare it to other z-scores, not other x bars. And z-scores always have, no matter what the shape, anything, the mean of the z-scores is always 0. The standard deviation of the z-scores is always 1. All right. You guys.
Sorry, I started speaking.
Okay. Now, let's go back to our picture of this, right? Like we started with we have an expectation. And if our sample is surprising enough, we don't conclude we conclude that expectation is wrong. Is everybody with me? So our expectation is that the mean is actually is less than or equal to 15. So if I conclude that's wrong, I'm going to conclude that the real mean is bigger than 15. What kind of samples? What would that say about our samples to make us conclude bigger than? Surprisingly bigger than. Well, they would be up here. Yeah? All right. So, we have something called a rejection region. And if our test statistic is in that rejection region, that makes us X out the null hypothesis and conclude the alternative.
Wait.
Okay. So remember we're saying if our sample is surprisingly big in this case, because my alternative is greater than.
Yeah.
Okay. So if my sample has this z-score,
Yeah.
that is surprisingly big. If my sample has this z-score, it's big, but it's not surprisingly big. Cool? So any z-scores in this area is going to make me reject the null hypothesis. Anything in this area is going to make me not reject the null hypothesis.
How big is that area?
That's a lovely question. The answer is, it depends, but I promise to tell you. So, in real practice, what happens is you actually start with how big do you need that area to be. And there's lots of things that when statisticians do this, they use to decide how big that area should be, okay? However, that is beyond the scope of this course. I'm going to tell you how big that area should be, and it'll change with the different questions. Okay, so what we do is we give you a value called alpha. This is supposed to be the Greek alpha. It's really hard to hand draw. I just draw, it's supposed to be like, I don't know, it's kind of like a fish. Alpha, okay? Or I might call it a significance level. Okay? So for this one, let's go ahead and say alpha is going to equal 0.2. And what this basically means, if our sample has a 20% likeliness or less, we're going to reject the null hypothesis. Okay? So,
Every case.
no, I'm going to give you a different alpha for each question. But I will tell you what that alpha value is. You guys, can we figure out this z-score? If I know that this area is 0.20, what is it?
Oh, yeah. So the alpha at the significance level is very similar to confidence level having.
The confidence level, well, so it's similar to, yes, the same no. Because, for instance, with that confidence level, this region is cut in half. Because it's like that middle percent and you have the other tail. By the way, this is what we call a right-tailed test. Can we see why this is right-tailed? Okay.
But can you also have a alternative hypothesis that's like on the left side that's like too small?
That's the next one. I'm doing an example of each kind of test. I very strategically chose these.
Okay.
You guys, what'd you get? 0.85 maybe? Okay, so that means after I'm going to calculate this z value for my sample. And if my sample gives me a z statistic of 1.2, 1.2 would be in the rejection region. So I'm going to reject the null hypothesis. If 1.2 is not in the rejection region, or let's say my z-score is 0.6, so it'd be like right here, I'm not going to reject the null hypothesis. So this z, and it feels weird now because we haven't done it yet, okay? This z is a measurement of your sample. And so if your sample z is too big, in this case, we reject the null hypothesis. If your z is not too big, we don't reject the null hypothesis. You guys, we have example upon example upon example of this. I know this is a very complicated reasoning process, okay? And I know that. I would not expect all of this to make total sense yet. Go ahead.
So for this one, we're rejecting the
So if I get a z-score that's bigger than this, I'm saying my expectation is wrong, right? Because it's so big, it makes me question my expectation. So it's the equivalent of a candy bar that costs $3. That was enough to make us say, oh, $3 is pretty far away. Mm-hmm. So this is like the how far away it needs to be to make us say that our expectation is wrong. Remember, $2.52 was arguable, but $3 definitely makes you think of this area right here as $2.52. Like how do you decide? This is like the deciding boundary between, is it far enough away for me to say something was wrong with my initial expectation? This region is the what is too far away. Does it help to think that way?
Yeah.
You need a boundary for that. Like how do you, I get my sample and I need to decide, was my original expectation wrong? There's got to be a boundary set somewhere for how crazy my sample needs to be to make me do that. That's what this is the boundary between I have a crazy sample or I don't have a crazy sample. All right. Now, the next one, our hypotheses were for right now.
So we don't have to like state right now which hypothesis we choose. Okay.
Because that's even more hairy, to be honest. Okay, you guys. Will this be a picture of a Z or a T? It's proportions. T only applies to means. Proportions are always Z's. Always. But I got great news for you. It's not going to be hard to remember, and let me show you why. The ones that say prop have a Z in them. Do you guys get what I'm saying here? All right. So Z's have a mean of 0, a standard deviation of 1. Lovely. Now, which samples will make us question if this is true or not? What would need to be true about my sample for it to make me question if this is true? It would have to be the sample where the percentage is big or a sample where the percentage is small. If I'm questioning, is this true or not? Like if I got a p hat of 50%, that's pretty good evidence that that the expectation is true. Yeah? Okay? So what needs to, like, my sample, in order for me to question this, would need to be smaller than 0.4. For me to question that original expectation, my sample would need to be smaller than 0.4. And if my sample was 0.39, I'm probably not going to question this. Right? 0.39 is pretty darn close. But 0.32? I don't know. 0.2? Probably would question. Okay. So, for this one, I'm going to do alpha equals 0.05. And like I said, every question I give you, I will give you this alpha. You don't need to figure out which one to use. Okay? And so now, should my rejection region be on the right or on the left? Left, because the p-hats that are going to make me say that this is wrong are the smaller ones, or that this is the correct one. Okay. You guys, that rejection region follows the alternative hypothesis. So, if my alternative hypothesis is a less than, well, less than numbers are on the left. If my alternative hypothesis is greater than, that would be on the right. Everybody good?
So if is that still gonna give me the? Do I have to do like the?
It's going to give you a negative number, yes?
Yeah, but I got negative.
You got what?
I got negative number.
Negative 1.2?
Negative 1.6.
Oh, negative 1.645.
Yeah. Oh.
All right, so if the z statistic from our sample is less than negative 1.645, we'll reject. Okay? We'll talk a whole lot more about what it really means to reject tomorrow.
Wasn't there something though with like in norm where you have to like right, middle, left?
Yeah, I have it on my.
Yeah, but I don't. So how? That doesn't matter for us because I got the same answer.
Correct. That is correct. I shouldn't have said right because we're talking about left, center, and right. You guys, my last one here. My null hypothesis was that mu is equal to 9. My alternative, we said, was mu is not equal to 9. And for this one, guys, I'm going to use alpha equals 0.01. Now, will this one be a Z or a T? T, because we don't have the population. It's about a mean, and we don't have the population standard deviation. Again, lots of time to practice this. I don't want you guys to get too bogged down in it, okay? And so if that's the case, T doesn't have a standard deviation. We need to give it a degrees of freedom. What would our what would that be? 33? And you got that by doing 34 minus 1, yes? Okay. All right, you guys.
My curve was really bad.
Got it. You guys. When my alternative is not equal to, this one looks a little bit different. When my alternative is not equal to, that means I'd be convinced with a sample that's too small or too large. So we call this one a two-tailed test. This one's a right-tailed. This one's a left-tailed. This one is two-tailed. And the combined of the tails needs to equal that 0.01. So this one is going to be 0.005. This is actually very, very similar to finding the values for a confidence interval. You guys, what are we getting? T, and what value did you get for T? Okay, you guys, that means this value is negative 2.733, and this value is positive 2.733, right? So they're going to be symmetrical. All right, that means we are going to reject if T is less than negative 2.733, or if T is greater than 2.733.